So let's look at some forecasting methods when you are making a short-term forecast. So we have a short-term forecasting horizon and we have relatively stable data. The first approach is the easiest of all forecasting methods. It's called the naive approach. The naive approach is when your next forecast is equal to, having technical difficulties here, is equal to the previous period's actual value. So the idea here is that if you're forecasting a period into the future, you simply use the previous actual number. So for example, if you're running or managing a bank and here's the number of complaints we are experiencing, and these are the number of complaints we're experiencing each year. So in year 1, we had 60 complaints at our branch, and at year 2, we had 65 complaints at our branch. Then the naive approach to forecasting would say our forecast for year 3 is that we will have 65 complaints. It takes the actual number from the previous period. So you use this when you have very stable or level data and you're going very short term. The benefit of this is it's super cheap to do, right? Anyone can take the previous year's data. It's easy for everyone to understand. You know where that number came from. It's easy to explain to stakeholders. It's also very quick and easy to prepare, right? We just grab the previous number and we're done. Now, this forecast is appropriate if the data is stable. So let's look at a couple scenarios here. All right, so let's suppose that this is your data over time. Okay. So we'll suppose that in period 0, let's go back a ways, that the number here is 70. And then in year 1, the number was 60. And then in year 2, it was 65. And we just forecasted that in period 3, it was going to be 65 as well. So notice that based on our data, it's a reasonable forecast. It's generally stable, it just wiggles around a bit between 60 and 70. So a naive forecast will work fine. But what if instead, in period 0, the actual number was 55, and then in period 1, it was 60, and in period 2, it was 65. Then making a forecast that uses the previous number, so us forecasting forward that it's going to be 65 again, this may not be the most accurate forecast because we're ignoring that trend, that upward motion, by simply taking the previous number. So the naive forecast is really used when your data is fairly stable, when it's just kind of wiggling around the same set of numbers. The benefit is it's cheap, it's easy to do and easy to explain, but it loses its accuracy quite quickly when there's any kind of pattern to your data. Now, the book references what is called naive with trend, and in which case they're saying, okay, well, if you previously have this trend, then the naive approach would be to continue on with the trend. When we look at naive, we're looking at it very much, naive in terms of it's very much definition term, which is when it's naive, it is just the previous period's number. We'll look more at trends and patterns when we look at our longer term forecasts. The second type of short-term forecasting is what is called the moving average. The moving average takes the average number of our recent actual values as the forecast for the current period. Okay. That average gets updated as we move further along in time. So the formula for forecasting with the moving average looks like this. All right, so don't let that formula scare you. Essentially what it is saying is it is an average because we have a sum of our actuals divided by n. So we need to make a decision. The decision we have to make is how many periods in our moving average. Is it going to be a 3-period or a 3-year moving average? Is it going to be a 5-year moving average, a 7? 3, 5, and 7 are pretty popular as number of periods. So what we're doing here, if we're doing a 3-year moving average, if we're trying to forecast period 5, then we're going to take the 3 previous periods and find the average of those. So our forecast for period 5 would come from adding up 65 plus 55 plus 58 divided by 3. So if we do that calculation, 65 plus 55 plus 58 divided by 3, and we get 59.3. So our forecast for the number of complaints in year 5, based on the last 3 years of complaints, is 59.3 complaints in the year. Now, if we want to forecast for period 6, then we need to know what the actual data was for period 5. The actual data for period 5 was 64 complaints. Then because it's a moving average, we're going to move and use the 3 most current sets of numbers, which is 64 plus the 58 from period 4 plus the 55 from period 3. So notice how we're now shifting to the newer 3 numbers for our moving average. So 64 plus 58 plus 55 divided by 3. Plus 55, and we get 59. So our forecast for period 6 is 59. Now, how far into the future are we forecasting? Notice that to forecast period 5, we need to know period 4. To forecast period 6, we need to know period 5. So right now with this moving average, we're only actually forecasting 1 period into the future, 1 year in this example. Well, what if you wanted to forecast 2 years into the future and none of those 2 years have happened yet? Well, if you're going to forecast into the future, and so if we were to do forecast for period 6, but we didn't know what the actuals were for period 5, then instead of using this actual 64 in our calculation, we would use the forecast for period 5 for our calculation. So instead it would be 59.3 plus 58 plus 55 divided by 3. And you can see then, what if we were forecasting multiple years in the future? Then each of these numbers starts to get replaced by the forecasted, and we begin to forecast with forecasted. What this does is turns your forecast into a naive approach, and you'll stop seeing that your forecast in the future, it'll stop changing. After a couple more periods, then the numbers all become the same. So it's a very short-term forecast method, otherwise it turns into the naive approach. Now, we chose a 3-year moving average in this example, but you don't have to. You could choose a different number of periods. So for example, we could do a 5-year moving average. Okay, so if we were to do a 5-year moving average, let's do forecast for 6. And let's do a 5-year moving average, in which case we use the previous year. So we use our 64 actual, if we have it, 58, 55, 65, and 60. So if it's a 5-year moving average, we go back 5 years instead of 3, and we divide by 5 instead. So if we do that, the number it gives us is 64 plus 58 plus 55 plus 65 plus 60, all divided by 5, we get 60.4. So you see how it changes depending on what number of periods we choose. So what difference does it make what number of periods you choose? It depends on how smooth you want your forecast to be. The more number of periods, the smoother it's going to be, because you're taking more data into consideration and it's kind of taking out the extremes and smoothing it out. If it's a shorter term moving average, then it's going to have more variation. So what you see here on this table on the right is that you see the number of complaints and then you see the moving average, and this is a 3-year moving average. When you start to do more years, then it starts to smooth out a bit because you're taking more of the ups and downs into consideration. Now, the benefit of the moving average is that it takes into consideration more data than the naive approach. 3 periods or 5 periods, whereas the naive included just 1. It's pretty easy to calculate. It's not too costly in terms of time. It does have a lag, so you'll notice here's the complaints and here's where it shows up in the forecast. So it does have that lag period. And the forecast will change depending on the number of periods you choose. So you need to decide how smoothed out or how sensitive you want your forecast to be to change. Now, when we do a moving average, the old values and the new values have essentially the same weight, right? In a 5-period moving average, everything is a fifth of the weight. This brings us to a different approach, which is the weighted moving average. And the weighted moving average is just like the moving average, but we can put more emphasis on more recent periods. So we can change the weighting of the data and more heavily weight more current information, because that's more likely to represent what will happen going forward than things in the distant future. All right, so let's look at how a moving average would work, a weighted moving average. So let's define it first. Here we have variation of the moving average. So it's just like the moving average, but more recent values are given larger weights. In calculating our forecast. So it's a variation of the moving average. More recent values are given larger weighting in calculating the forecast. So when you do a weighted moving average, you have to make some decisions. The first decision is the number of periods. So just like with the moving average, this time are you going to do 3 periods, 5 periods, 7 periods? And then you also have to decide on the weights. Your weights need to add up to 100%, and there needs to be some rationale for it. So if you're doing a 3-period moving average, 50% for the most recent because it's most likely relevant, and then how relevant things are to the future decreases the further out, so that's why we have the 50, 30, 20. So to find the forecast for period 5, what we do is we take our weight, so here 50%, and we're going to multiply it times the number of complaints in the most recent period. So we're forecasting period 5, we're using period 4. And then we have 30% times the actual from period 3 plus 20% times the actual from period 2. So notice I don't have to divide by 3 because by putting these percentage weights on it, it's already allocated to each of the complaints. So let's find that calculation. So we have 0.5 times 58 plus 0.3 times 55 plus 0.2 times 65, and we get 58.5. Okay. Now, when we want to go and forecast period 6, if the actual for period 5 is 64, then the 50% weighting is moving on to the 64. If you don't have an actual for period 5, then you're going to use the forecasted. We would put a 50% weighting on the 58.5 instead. All right, so 50% on the recent period, which is period 5, plus 30% on period 4, that's the 58, plus 20% on the 55. So notice how the weightings have moved, and now the 50% is on period 5 instead of period 4, and the 30% weighting is on period 4 instead of period 3. So the weightings are going to continue to move as you're forecasting forward. So that's 0.5 times 64 plus 0.3 times 58 plus 0.2 times 55, and our forecast there is 60.4. Okay. So the weighted moving average is a little bit more complicated than the moving average, but it has the additional benefit of allowing us to put more emphasis on the more current period of time. So here on this graph, you can see the weighted moving average versus the actual, and this is with a 3-period weighted moving average using the 50-30-20. The benefit of a weighted moving average is it includes more data than the naive approach. It's still not complicated to calculate, and it has the benefit over the moving average of that additional weight on the more recent. It's going to be dependent on the number of periods you choose, so you choose 3, 5, 7, something along those lines, depending on how smoothed out you want your forecast, or whether you want it to respond to actual changes in terms of big up and down changes, or whether you want it to be more smoothed out. There's always going to be that lag, and the choice of the weights are somewhat arbitrary, so someone might choose different weights. You should always be able to give a rationale as to why you chose the weights that you did. So we had the naive forecast, which was the easiest. Then we had the moving average, a little bit more complication, a little bit more accuracy if we start to see changes or patterns. Then we have the weighted moving average, which a little bit more complicated, allows us to put weights on more recent time. And then the fourth method we're looking at is what is called exponential smoothing. So exponential smoothing adds a bit more complication on top of the 3 previous methods we have discussed. With exponential smoothing, it's going to be a weighted average based on the previous forecast. And the difference between the exponential smoothing and the other methods so far is that it's not just the previous forecast, but it's going to also be a percentage of the difference between the forecast and the actual. So the exponential smoothing method is essentially allowing us to update our short-term forecast by considering how off we were from our previous forecast. So here's the formula. The forecast for a period t is equal to the forecast from the previous period, so t minus 1, plus, and then we have an alpha. The alpha is what is called a smoothing constant. And this is how much you want to adjust the previous forecast based on how off you were from that previous forecast. So what we're doing is we're taking what we call the forecasting error, right? The difference between what we actually had and what we forecasted. And this is both for the previous period. So how far off were we in the previous forecast, and then how much of that do we want to take into consideration? So alpha can be anywhere between 0 and 1. Let's look at a scenario where alpha is 0.4. Okay? So let's say we want to forecast for period 4. Well, when you are using the exponential smoothing method, there are some decisions you're going to have to make. You're going to have to choose your initial forecasting method. Okay. So when you're using that previous forecast, at some point you need a starting point. Then the other thing you need to decide is what your alpha is going to be. And we'll look more about that in just a moment. Okay, so let's forecast, all right, let's forecast period 2. And we're going to use the naive approach. You could use a different one, but we'll use the naive approach. And so the forecast for period 2 is the forecast, or is the actual from period 1. Which means when we go to forecast period 3, we're going to use our forecast from period 2, that's the t minus 1, which was 60, plus, and then if we look at an alpha of 0.4, we can then compare the actual for period 2, which was 65, to what we forecasted, which was 60, and you can see we were off by 5 points. So then we want to take that into consideration for the next forecast. So we're going to adjust the forecast by the fact we were off, and so the alpha allows you to choose how much that adjustment is going to be. If your alpha is 0, this was 0, then you're making no adjustment at all. You're not even taking into consideration your forecasting error, or how off you are. If alpha is 1, then you're fully taking into consideration that forecasting error, and all of that error, all 5 we were off, would get added to our forecast. So we go from 60 to 65. Okay? Now you may choose to not fully incorporate the error, because you recognize that in the future, maybe higher, maybe lower, so you're only partially incorporating that forecasting error, and that's going to create a smoothing effect, which is why this is called a smoothing constant. So it really comes down to how responsive you want that forecast to be. Do you want every increase to be reflected in the forecast and every decrease in actuals to be reflected in the forecast? Or do you want your forecast to kind of take into consideration the ups and downs and be somewhere in between? So how smooth do you want it to be? The closer you are to 1, the less smooth. The more you are taking into consideration every up and down. The closer to 0, the more smooth it becomes. And if it's an alpha of 0, essentially you have your naive forecast. So let's look at an alpha of 0.4. Common alphas, often people use alphas of 0.05 or of 0.5. Okay, or somewhere in between there, depending on how responsive you want to be. So if it's 0.4, then we're going to take our forecasting error of 5 and multiply it times the 0.4. So essentially we're going to take part of that error, and that's 60 plus 2. So our forecast now for period 3 is 62. So then our forecast for period 4 takes the forecast from 3, which was 62, and then we have our smoothing constant of 0.4, and we compare the 62 that we forecasted for year 3 to what it actually was, which was 55, and we can see that we have forecasting error. We're off by 7, and notice this time the actual is much less than the forecasted, so now we have a negative forecasting error. So this becomes 62, and we have 55 minus 62 is our negative 7, and we're going to multiply that times our 0.4, and that gives us our negative 2.8. So 62 minus 2.8 is 59.2. So our forecast for period 4 is now 59.2. We could go on into the future, forecast 5. Our previous forecast was 59.2. We add in that smoothing constant times our forecasting error. In period 4, you notice the actual was 58. Subtract what our forecast was of 59.2. Notice again the actual is less than the forecasted, so 58 minus 59.2 is a negative 0.12, and we're going to multiply that times 0.4, so we get 59.2 minus 0.48, which is 58.72. Now notice with this method, every time we forecasted forward, we had the actuals from the previous year determine the forecasting error. What if you were forecasting 5 years into the future and you didn't have any of those actuals from the 5 years to put on there? If you don't have the actual, you have to put in the forecasted. So what happens is this thing quickly becomes a naive forecast because you can't measure your forecasting error without the actuals. And so if you're forecasting more than a period into the future, it's going to turn right back into the naive method. So naive, moving average, weighted moving average, and exponential smoothing are all very short-term forecasting methods. In fact, they essentially just forecast one period into the future. Otherwise, you're forecasting with forecasting, which you can do, and it only really works if your data is very stable, not a lot of movement. These are for very short-term decisions for data that doesn't have a lot of movement in them. So with the exponential smoothing, you're going to have to choose that starting forecast. You're going to have to choose your level of alpha. So what's the trade-off between responsiveness and how smooth you want it to be? What you're seeing here on the graph is the alpha of 0.4. The bigger the alpha, the more every turn is going to show up in your forecast. The smaller the alpha, the more smoothed out it's going to become.